last name. Thanks, Avi, for inviting me. I've never been here. This is my first time. It's a fantastic place. Yeah. My last name. It's very easy. It's divide and conquer. That's the key to. It's Vaikuntanathan. Nathan is not like your American Nathan. It's a slightly different accent, but other than that, you're good. You know, I shouldn't have. I got this question so many times that I put up this this audio file on my homepage. But yeah, this is it. Okay, good. So today's talk is about secret sharing and breaking the circuit size barrier in secret sharing, and so other questions in information-theoretic cryptography. So really, you know, to understand this talk, you don't need to know anything in cryptography. In fact, probably it's better that you don't. My point is that you know, many questions that come up in information-theoretic cryptography are really questions about you know, other sort of things in disguise, like locally decodable codes, monotone circuits, lower bounds, upper bounds for these things. So, you know, one point of this talk is to actually, hopefully, convert some small fraction of you to sort of start thinking about these questions. Good. So this is it. So let me start with this timeless quote attributed to Silvio. It's in a paper of Joe. You know, cryptographers don't sleep well, and for a good reason. You know, much of what we do in cryptography, you know, is only good against computationally. It makes the assumption that adversaries are polynomial time bounded, and on top of that, you need very special kind of computational hardness assumptions to make these things to make these things even stand up. Right? You know, they are not sort of P not equals NP, rather sort of that factoring this very specific like algebraic problem does not have polynomial time algorithms. In fact, it does have quantum polynomial time algorithms. So do you really believe it? I'm not so sure. That's why today we are going to switch to information-theoretic crypto, which you know, which gives us unconditional security. So you don't need to make any of these assumptions. In fact, it's even better. It gives you security against computationally unbounded adversaries. So no assumptions of, no computational assumptions of any nature. The question is, what can you do with you know, such strong sort of guarantees? In fact, a fair bit. You know, Shannon's work from the 40s was, you know, its work on information theory came after the work on one-time pads, if I get the chronology right. It was influenced. I was a faculty member at MIT.
Yeah,
but before, a bit, yeah. Here you go. So secure communication is just a question of, can I send a number, a message to you without sort of people in the middle learning. I want to encode the message in such a way that people in the middle cannot learn what I'm sending. So one-time pad solves this problem. In fact, one-time pad solves this problem optimally. Right? So that's more or less settled. And this really sort of was inspiration for sort of defining sort of information theory, so on and so forth. Secure computation, on the other hand, is a much richer sort of framework. It's not just sort of sending messages back and forth. It's a question of sort of computing functions on inputs that are distributed across many people. So there are many facets of secure computation. You know, again, sort of this study has contributed to sort of theoretical computer science at large, which has nothing to do with sort of privacy or cryptography or anything of that form. Multi-proof or interactive proofs, where if I, you know, I don't want to invent history, but I'll defer to Avi, was invented for the purpose of constructing zero-knowledge proofs for all of NP. Is that right, Avi?
It's
part of it. So they did that with Avi and Shafi and Mickey Benor and Joe Killian, and this model, you know, after lots of sort of important work, became sort of PCPs and approximability and so on and so forth. I'm going to talk about today. What I want to talk about is two other primitives in information-theoretic cryptography, which has been well studied. And connections between these two primitives, and these are secret sharing and private information retrieval. Okay, so let me start by defining what these creatures are. So here's secret sharing. You have n plus 1 parties. N is n small parties and one big guy called the dealer. The dealer has a bit, as one bit B, and his goal is to distribute this bit across these players. So in other words, sort of take this bit, compute a randomized function of this bit, get many bits, and distribute it across these 5 people in such a way that later, when some specified subset of people come together, they can reconstruct the bit B. So for example, you might want that any set of 3 players here, 1, 2, and 3, should be able to put together their information and reconstruct and compute the bit B. On the other hand, no 2 people, if 1 and 2 alone come together, their shares should be statistically independent of the bit B. Yeah, so that's the kind of thing you want. And of course, you can define it very generally. You can define the set of authorized subsets of players. Yeah, so any authorized subset should be able to reconstruct the secret, and no other subset should be able to reconstruct. Yeah, so this is secret sharing in its generality. So the first thing I said, any 3 people can reconstruct, no 2 is threshold secret sharing, right? So that corresponds to the set of subsets of size at least t being the authorized subset. And of course, you can define it very generally. You can any monotone function gives you a set of subsets of n parties that should be able to reconstruct. Why monotone? Because if a set of people can reconstruct the secret, any superset can also do it. Yeah. So the set of subsets of 1, 2 up to n has to be closed under taking supersets. Yeah. So that's that, and this is 1-to-1. Yeah. Any monotone function implies an access structure. Any access structure is a monotone function, basically. Yeah. So is the question, is the problem clear? Yes? Too slow? Too slow, too fast? Too slow. Okay.
So if it's not authorized, then even given all your information, the bit is still a fair coin flip?
Yeah. That's right. That's what I want, indeed. In particular, imagine that you have an unauthorized set, right? Look at the probability distribution of its shares when the bit is 0 versus the bit is 1. They should be the same random variable. They should be identically distributed. Yeah.
At this point, it's not clear that you can even do it.
Can even do it. Yeah, that's right. That's right. Exactly.
Just to be exactly the same random variable, or maybe just closing.
You can define it either way. It doesn't quite matter for most purposes. Certainly not for what we are talking about today. Yeah. So what have we said, right? I mean, it's not clear that you can actually even do this. Yes. So if I give you 10 minutes, you will come up with a way to do it, with some way to do it, yeah? Maybe even 5 minutes. For me, 5 minutes. So how do you do it? You enumerate all the subsets, all the authorized subsets. For each authorized subset, you do the following. You pick, so let's say the subset has 5 parties. You pick 5 random bits whose exclusive OR is the bit B that you want to share, and give these bits to each one of the parties. Right? So that's for one authorized set. For another authorized set, do this again, completely independently. Yeah, so you can do this. So yeah, so it's feasible to do this. The question we are going to ask is the question of this we have said. The question we are going to ask is the question of complexity of secret sharing. And to me, complexity is the total size of the shares, the information that I'm giving all these parties. So what we just did, right? The total number of bits is the number of subsets in the access structure times the size of the access structure, sort of. So it's more or less the number of sets in the access structure, which could be as large as 2 to the n. Right. In fact, even for something as simple as a threshold access structure, which says any set of size n over 2 is included. Yeah, any smaller set is not included. Still, how many sets of size n over 2 are there? Roughly 2 to the n, right? So this simple secret sharing scheme could actually be quite bad, even for relatively simple to describe access structures. Right? You can do better. There is a work of Benello and Leichter who showed that if the access structure can be recognized by a small monotone Boolean formula. What do I mean by this? there should be a small monotone Boolean formula which takes as input the subset, which is a characteristic vector of the subset, and says if it is authorized or not. That's what I mean by recognized by a small monotone Boolean formula. So if the access structure is such that it can be recognized by a small monotone Boolean formula, you have a good secret sharing scheme. What do you mean by good? The total size of the shares is proportional to the size of the monotone Boolean formula. That probably needs another 5 minutes for you to reconstruct, and in fact I won't do it now, right? But not that hard at this point, I mean, in retrospect. Good.
Is it upper or lower bound?
It's an upper bound. It's an upper bound. If you have if the access structure is recognized by a monotone formula of size S, then there is a secret sharing scheme. The total size is S.
Is there a match and lower bound if players are also bounded?
No. Where the players are what? Say again?
If you bound the players computationally.
Computationally. Oh, I'm never going to sort of get into that. So there isn't. That's a short answer. And I'm not going to get into the right. I mean, so if I bound the players computationally, I'm getting into the sort of the assumptions, cryptography, one-way functions, or I don't even know one-way functions at this point.
No, the scheme has to be information-theoretically secure, but players cannot do crazy things. So you can at least you can compute the access function.
Of course, the players are computationally unbounded, right? For the upper bound, the players have to compute the formula. So it's not that crazy.
So what is the lower bound in the first box?
There is in the first box. Yeah. Okay. So I'm saying, if you look at this scheme, how does it perform for the worst possible access function? I mean, we know that there are formulas, there are functions with formulas of size 2 to the n, Shannon counting, right? And that. So it's not a lower bound on secret sharing schemes. That's probably what you were asking. It's a lower bound on this particular scheme. Yeah, that's right, exactly. There aren't lower bounds for general schemes. That's sort of the point of what I'm going to get to. Good. So is monotone Boolean formula size the lower bound? Not really, and that's the work of Avi and Mauricio Karchmer. They defined this model called span program, in particular monotone span program. Again, they showed that if the function is recognized by a monotone span program of size S, there is a secret sharing scheme of complexity S. Yeah, and monotone span programs are a more general model of computation than Boolean formulas. So this is a more general result. And again, if you ask the question, and this is the question I'm going to ask, what is the complexity of, what is the size of the monotone Boolean formula, monotone span program for the worst possible function? This is the question I'm going to ask. And that is, the best of my knowledge, that was 2 to the n. Avi, you have to correct me if that was the best possible, that was the best known. And the lower bound, again, Shannon counting gives you 2 to the n over 2. So it's not quite exactly tight, but both of them are exponential. Yes?
So what is the condition again here? So this lower bound is unconditional?
No. This lower bound is not for a secret sharing scheme. It's for a monotone span program size. Right? The upper bound says for every function, there is a monotone span program of size 2 to the n, size however you define, the right way to define. And lower bound says there exists a function, no explicitness at all, that has monotone span programs of size at least 2 to the n.
But you could imagine, what's the best known lower bound for secret sharing?
You're asking questions that are two slides. Okay, here you go. Yeah, that's the lower bound. So the question is, you have both these schemes are tied to a particular computational model, so, and the cost of communication, in some sense, the share size is a measure of communication. And somehow the measure of communication depends on a measure of computational complexity. This is not out of the world. We know other examples of this nature, but still, it's a bit grates you, right? Doesn't sound right, at least to me. Yeah, and to Mark's question, the best lower bound on secret sharing schemes without any, just lower bounds on secret share sizes of general secret sharing schemes is n squared over log n. Okay, so upper bound 2 to the n roughly, 2 to the n, lower bound n squared over log n. And if you look sort of, if you dissect this Sharma's result and look closer into it, there are elements of formula lower bounds, from the 60s, I confused the three Russian names. Nechiporuk, exactly. The n squared, the Nechiporuk n squared lower bound. This lower bound has the elements of it.
It's an explicit lower bound.
It's an explicit lower bound as well. Good, right? So he shows an explicit access structure for which, exactly.
But it's also the best for non-explicit.
That's right. Okay, so if you guys keep anticipating my bullets or slides or whatever, so you can simulate my talk. Yeah. We don't know any better lower bound, even existentially. We don't even know how to show that there exists an access structure which requires shares of size more than n squared. And this is like, I don't often say that we should, as cryptographers, be more embarrassed than complexity theorists, but this is a situation where we don't even know how to show a non-explicit lower bound. Counting argument fails. You can try to do it, but completely fails. Right. So that's what it is. Now you could define a class of secret sharing schemes, which are what I'll call linear secret sharing schemes. Sort of says the function that takes a subset of shares and outputs the bit, the secret bit, is a linear function. It's a linear function. These are equivalent. I think if you have this condition, then I think you can actually make. So what's about these functions are linear functions? If you restrict secret sharing schemes to be of this form, then Avi's result, Korchmar-Wigderson, showed that the complexity of secret sharing scheme, linear secret sharing schemes, is tightly related to the complexity of the size of the monotone span program that computes a function. They are, in fact, there is a relation between communication complexity and computational complexity for linear secret sharing schemes. And again, because of what we know about monotone span program, there is a 2 to the n upper bound versus 2 to the n over 2 lower bound here. Right, so this is an actual lower bound on secret sharing schemes, except only for linear secret sharing. And this is maybe what you were asking. So even for computationally secure secret sharing schemes, this is the best known. Yeah, I mean, I don't know anything better than 2 to the n. Even if you restrict.
My question was,
yeah,
somehow if any reasonable schemes for cryptographers would have the reconstruction be efficient.
Yeah.
And to rule those out, it's like circuit lower bounds.
Yes, that's right. So I mean, on the face of it, right? So that's why I don't want to get into sort of, there could be a regime where reconstruction is possible, but computationally inefficient because of circuit lower bounds. I don't want to get into that regime. I want to sort of ask the pure question of communication. I don't want to ask computational. That's why I was skirting this question. Thanks.
But if you believe in circuit lower bounds, say you're willing to assume circuit lower bounds, then
are there secret sharing lower bounds?
A hard function. If a function is hard, then it's impossible.
Good. So it's easier to prove lower bounds against computationally restricted reconstruction functions. But even that, we don't know how to prove. Yeah, we don't know how to prove anything.
It's a different question. I mean, we have exponential circuit lower bounds existentially, and we have only quadratic lower bounds for secret sharing.
Yeah, that's right.
But those exponential bounds correspond to something like you either need exponential communication or the reconstructors need exponential circuit size.
You ask whether circuit lower bounds suffice. They don't suffice because we have them existentially.
But for monotone.
We do not have them for.
That's right. Somehow the reconstruction is a very non-monotone operator. So these shares could come from. There's no restriction on the reconstruction function to being monotone, and therefore I don't know how to. Yeah. I don't think people have asked this question, and again,
It doesn't stand to reason too much, right? Because you're talking about statistically independent events, so it seems like more, the computation would be some, equation more in some field.
So I guess one way to answer. So one way to answer this question is that if you look at the known secret sharing schemes, the reconstruction function is sort of a linear function over a field. So it's field of size 2, let's say. So it's very non-monotone. So If you prove a lower bound for monotone reconstruction function, it's unclear what that means, because even the simplest secret sharing schemes we know are sort of non-monotone. So yeah, I don't think people have asked this question, and maybe for this reason. Good. So this is the state of affairs. Terrible lower bounds. The best upper bound is 2 to the n. Yeah. Okay. So this is our result. We show that for every access structure on n parties, there is a secret sharing scheme with share size less than 2 to the n. Okay, so and that is 2 to the 0.994 times n. So usually in theory talks, 0.994 is a proxy for 1 minus epsilon, right? This is not 1 minus epsilon for an arbitrarily small epsilon. No, this is not 1 minus epsilon. This is really 0.994. Okay, so this is our result. Okay, so I shouldn't have called, in retrospect, the talk breaking the circuit size barrier. It's a crack in the circuit size barrier, but it's a crack that shows that you're doing something different than writing a monotone span program or a monotone circuit for this access structure and going with it, doing something for every gate or every sort of unit of the circuit. You're doing something completely different here, and there is hope that the 0.994n could become potentially little o of n. Okay, so that's and so when I give this talk, and the people in the audience, they keep thinking, from this slide on until the time I explained where the 0.994 comes in, this question keeps in your mind, what is this 0.9? So let me actually break it down for you right away. Okay, so here is a question that we ask. You still want to write down a small monotone formula for all monotone functions, except it's not going to be over the and/or basis, because we know and/or basis you're dead. You have 2 to the size 2 to the n. Yeah. I'm going to augment this by slice functions, and slice functions are the following functions, right? So these are the class of all functions. Let's say for a moment n over 2 slice functions, right? So these are all functions which output 0 on inputs of Hamming weight less than n over 2, 1 on Hamming weight more than n over 2, and in the middle they can be as whatever they want. So there's a class of 2 to the n choose n over 2, yeah? So n choose n over 2 many numbers, 2 to the n choose n over 2 many slice functions. I'm going to add all those guys to the basis. Yeah, so that's a huge basis. Counting argument gives you nothing, no lower bounds. The question is, can you actually build a monotone formula for over this basis?
You can, of course you can. The question is whether you can use it to secret sharing.
Well, actually, is that obvious?
That you can build, you have more functions. If you can build formulas from else and else, you can build them also from there.
But I want to build this formula for every monotone function, and the formula has to have of this size.
So
Yes. Right. Good. So we do it.
It can be built.
Okay. I forgot that I'm giving the talk at IAS. So, yeah.
You said it's how to get it to the middle of n. You mean to get this also to
this?
the middle?
Yeah. I don't know any barrier for Yeah. I'm setting my goals relatively low.
Potentially polynomial.
Potentially polynomial. I don't know any lower bounds. So what we do is, yeah.
Think t equals n over 2, or t is allowed to vary?
T is allowed to vary as well.
So isn't any Boolean function just an or of n
No.
function?
No.
I see.
No. We can sort of get into it, but no.
Why doesn't counting give you some lower bound?
Counting doesn't give you anything, right? Because the number of functions in your basis is 2 to the n choose n over 2, right?
So
Most of functions, yeah. Right, so it's 2 to the n over root n. Maybe it gives you a root n lower bound, something like that.
So where are we going with this? We're trying to show.
Where are we going with this?
Here about monotone. If you have
Good.
small size under this, then
Good. That's the statement. Yeah. So what I was going to say is our 2 to the 0.994n comes in as an answer to this question. Namely, for every monotone function, we show a monotone formula, in fact, over this basis that has size 2 to the 0.994n. Once you have it, you have a secret sharing scheme, as we will show in a few slides. And if you can make this better, you can make the secret sharing scheme better.
okay, so you need to show that you have this
Correct.
Plus you need to show that the theorem holds for this complexity. Because you know if you have
Plus, he has to build a secret sharing scheme when
Right.
the given formula has this
yeah,
gates
he
in
needs
it.
to
Yeah.
repeat the theorem with this.
Right. Yeah, it doesn't. It's not black box, but this is sort of a moral statement, right? If you make this number, if you make the answer to this question 2 to the square root n, you will get 2 to the square root n size secret sharing scheme.
So hold on. So if you have a formula of size s, you can still encode it with roughly s bits, no?
But it's not clear
Yeah.
if the gates are of this nature.
When
But I
Okay,
know.
so
Yeah,
then
that's right.
so slice is just you have some inputs, you know what they are, so it takes like t bits to encode or t log n bits to encode.
These functions are arbitrary on.
This is arbitrary on the middle layer. The function to describe it takes
Right.
you to
I
the
see. Okay. Yeah, these are arbitrary. Yeah, that's right.
Oh,
Yeah. So just look at n over 2. You have all possible like 2 to the n choose n over 2 function at your disposal, right? And now what do you do?
Your shorts.
Say again?
Your shorts.
Yeah, I'll show you. Good. Excellent. Okay, good. Yeah, okay. That's we can also get a better linear secret sharing scheme from the same sort of from the techniques used in the proof of this theorem. We also get a linear secret sharing scheme. The best known was 2 to the n. We get 2 to the 0.9999. It's really 0.999, 0.998 da 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 da. Yeah. Okay. Good. So. And the corollary of this is that is a statement which has nothing to do with cryptography. It has something to do with the size of the best monotone span program for arbitrary Boolean function, arbitrary monotone functions, and that is 2 to the 0.999. And the best known, to my knowledge, was 2 to the n. Yeah, and the lower bound is 2 to the n over 2. But just to say, in this for monotone span programs.
For the non-complexity theorists, what
Yes.
is monotone span program?
It should be for complexity theorists. I mean, it was okay. So
Not
I need.
everybody in the audience is a complexity theorist.
Ah.
Some are quite far.
I see. So can I write here, and would people
Yeah.
see? Okay, good. So monotone span program is the following model of computation. It's Avi's model of computation. So you want to you have a function f you want to compute. Yeah. So you compute it in the following weird way. Okay. So you create a matrix m sub f over some finite field. You label each of the rows of this matrix by a variable or its negation by literal. Okay. So x1, x2 complement, so on and so forth, and things can repeat, blah blah blah. Yes. And on input x, on input some alpha in n, so f is from n bits to 1 bit. What do? You pick a subset of the rows of this matrix, right? So m sub f comma alpha is a subset of the rows of this matrix indexed by the bits in alpha, the ones that alpha says is true. So the question is, f of alpha is 1 if and only if a particular vector, let's call it 1, 0, 0, 0, the unit vector, is in the span of m sub f comma alpha. So this is what you want. So in other words, you want to take a function, you want to create a matrix of this form which has this property. Yeah? And that's a span program. A monotone span program just does not have literals, it just has variables in it. And of course, you can only compute monotone functions using it, but yeah, that's. Right.
And the size is the number.
The size, good. So the size of m sub f is the number of rows. Yeah. Counting argument tells you that the number of rows times the number of columns is 2 to the n, just counting. But the number of rows could be as small as 2 to the n over 2. And that is actually the size. So why are we counting the number of rows? Because that is exactly the size of the shares, the sum of the size of the shares in a secret sharing scheme. You don't care about the columns. Yeah. Good. Good. So I want to mention this this result of Tony and Robert and a bunch of others who show lower bounds of the form 2 to the omega n. So this is the non-triviality here is that these are explicit lower bounds, because non-explicitly 2 to the n over 2 is a lower bound. Yeah, they show explicit lower bounds of the form 2 to the omega n for certain functions, for monotone span programs. Yeah. So all this. So after this sentence, everything here relates to linear secret sharing schemes. And what I'm trying to say is that even for linear secret sharing schemes, there is a gap. We close the gap. Well, not close. We slightly improve the gap from 1 to 0.99, but there's still no. Yeah. So good. So that's what that is. All right. So let's see how to prove the theorem. Yeah. So the proof follows in 3 steps. I'm going to define a game called the conditional disclosure of secrets game. And I'll use it to create secret sharing schemes for a class of access structures. It won't not nearly be the set of all access structures. It will be a non-trivial scheme for a class of access structures. And this is really the part that I want to focus on in this talk. If I don't get to any of the other parts, I'm not sad. In fact, I'm quite happy if I tell you the proof of this theorem. And this is where the connection to 2-server private information retrieval comes in. 2, we want to make this from a 2-party to a multi-party game. I haven't told you what this game is, but I'll make it into a multi-party game, and that'll sort of give us, an even larger class of secret sharing schemes. The first step used Zaev as a black box. Here I have to open Zaev's head and actually mess with it and to get this. Yeah. Say again? And Gopi, yeah, that's right. But I prefer messing with your head then. And the final step is to actually take these things into a secret sharing scheme for all. So this is actually the proof of the monotone circuit, the monotone formula theorem over the slice function basis. That's this, basically. Yes.
So why doesn't the slice case imply the general case with the penalty factor n?
I don't see.
Can't you separately? Oh, I see. Because a slice n. Oh, you have to have an and on top.
No.
It could be monotone, so.
Yeah, it's just so that it's not well.
It's not clear. Okay.
It's not clear. Yeah. We can try it, but I prefer that you try it. And yeah, you'll try it. Yeah. Okay, good. So this is what the very first step is what I want to focus on in this talk. Right? So here's the game, which I'll tell you in a minute how this is connected to secret sharing. It's called conditional disclosure of secrets. Here's the game. You have 3 parties, Alice and Bob and Charlie. Alice has an input y, which is an n-bit input, and a bit b. Yeah? And Bob has an x and a bit b. X, again, an n-bit string and a bit b. And Charlie has y and x, but he just doesn't have the bit b. That's it. And Alice and Bob share this common random string, which Charlie cannot see. So this should be a line here that this guy cannot see what's up there. Okay. And what are they trying to do? Alice and Bob are trying to send a single message to Charlie, no back and forth, just a single message to Charlie, at the end of which I want one of 2 things to happen. Either f of xy equals 1, in which case Charlie should be able to compute the bit b given m sub a and m sub b, or f of xy is 0, in which case m sub a and m sub b together should have no information about the bit b, again in a statistical sense. The joint distribution of these bits, these values, these strings, should be independent of the bit b. That's the property I want. So yeah, this is a bit of cryptography. There are 2 things. There's correctness, which says that if f of xy is 1, what should happen? And privacy, which says if f of xy is 0, what should happen? Yeah.
It's the same type of
it's the
condition.
Same type of condition. Yeah.
Secret sharing.
That's right.
If something holds, if the access.
You should get the bit,
yeah.
Otherwise you should have no information about the bit. That's what it is. Yeah. So this is a game. It's sort of like a number in the forehead game, right? If you look closely at it, any party knows 2 of the inputs, but not the third. Yeah. And there is a particular communication pattern that we care about. And we'll see how this is related to secret sharing in just a minute. Okay. So it's been studied for 20 years. Good. So how is this related to secret sharing? So I claim that if you solve this problem, you get a secret sharing for a particular class of access structures. They're called graph access structures. What is a graph access structures? The set of parties is a set of nodes in a bipartite graph, right? N by n. You should think of capital N as 2 to the little n. Yeah? Little n is a bit length of these vectors. And this graph corresponds to an access structure. Why? The set of edges is the set of pairs of parties that can reconstruct the secret, right? And if you don't have an edge, you can't. We'll call this a forbidden graph access structure because I'll let every triple of parties to reconstruct the secret. So you say, if you have 3 people come together, you can always reconstruct the secret. If one person comes by himself, you can't. And if 2 people come together, well, depends on whether there's an edge or not. So this is a slice function, if you think about it, right? The slice is a 2-slice function, if you think about it. Okay, so if you have a solution to the forbidden to the CDS problem, you automatically get a solution to a secret sharing scheme for this class of access structures. Is what I want to sort of convince you. And this is you need to sort of think a little bit to work through the details, and that's that. So how do you do it, right? You want to share a bit B. I'm a dealer. I want to share a bit B. I give each player on the left-hand side the Alice message for her ID. Each player on the right-hand side, I give the Bob message. And if 2 people come together, yeah, they have exactly one Alice message and a Bob message, and whether they can reconstruct or not depends on whether f of x, y is 1. Yeah, that's that. So it's a very natural sort of formulation of secret sharing for graph access structures.
The complexity is the length of MA and MB.
Yeah, exactly. Yes.
Why does 3 every 3 can reconstruct?
Why every 3? Because if 3 people come together, right, they get 2 of Alice's messages, right, on 2 different inputs with the same, reusing the same R in the sky. So CDS does not talk about what happens if Charlie can rewind Alice, can say, look, Alice, I got your message. I'm not happy. Send it to me for a different input. It could completely break. There's no guarantee if.
You want it to break.
I want it to break. So I can actually make it break by doing a 3-wise secret sharing for all parties. Yeah, so that's easy. On top of that, a threshold secret sharing scheme, which is easy to do, so why not? Okay, so I think of it as my inability, and this is sort of a stupid fix to my inability. Yeah. Good. So this is what it is. Yeah. So CDS is an interesting problem for what we are trying to do. Good. So we'll think about CDS for the class of all functions, in particular the index function, right? Where one of the inputs is an array, is a database, it's a function, truth table of a function. The other input is an n-bit string that indexes into this. Yeah, so that's what. So really, if you think about it, right, what does Charlie not know? Just 1 bit. He knows everything else. He knows the truth table. He knows the input. There's 1 bit that Charlie doesn't know. And so why can't sort of Alice or Bob send it to them? Well, because they don't know whether he's allowed to get this bit or not, right? Whether he's allowed or not depends on both my input and Bob's input. So what do I do? Okay, so the best for this for CDS is 2 to the n over 2, which we'll see in just a minute, and the best lower bound is omega n. So again, roughly the same story as before. Good. So let's see actual protocols. Okay, so I want to sort of show a protocol. I want to solve this problem one way or the other to begin with. Forget complexity for a second. Yeah. So how would I do this? Okay, here's a scheme. I'll show you 2, in fact 3 schemes. Here's what I do. Bob says, let me take my x. I'll expand it to a unit vector sub x, right? And I'll one-time pad it with R. Okay, so I have R. R is very large. It's 2 to the little n number of bits, right? So I'm gonna take E sub x. Yeah, R plus B E sub x. That's what it is. So if you think about Charlie looking at this, he sees nothing, absolutely nothing, right? Because the whole thing is R. He doesn't see R, and this is random. So what does Alice send to help him out? She sends the inner product of the database with R. That's what she sends.
R is some shared source of randomness.
Shared source of randomness between Alice and. So if you think about sort of secret sharing, right? It's a random dealer in the secret. So right, the dealer is the one that implements both Alice and Bob. So
it's another vector, binary vector of
2 to the n. Yeah, that's right. Exactly. Yeah. So this is what it is, and I claim both correctness and privacy. Yeah. Correctness. Why? Because Charlie takes this string, takes the inner product with D, and what he gets is D inner product R, which he can XOR out with sort of Alice's message. And what remains is D inner product B times E sub x, which is B times the D of x, the xth entry of D. That's precisely what you want. If that is 1, you get B. If that's 0, well, you didn't know what happened. Yeah. So that's what it is. Which is
You can get from it also a span program for the index.
That's right. That's right. Precisely. Yeah. Yes. In fact, well, one could go back as well, of course, right? Good. So privacy, I want to be a bit careful. So you can't, these things you cannot sort of sweep under the rug. You have to be, you have to cross your I's and dot, well, the other way around. Yeah. So good. So why privacy? So we're looking at a setting when D of x is 0. Right? That's when, Charlie should not learn anything. What happens to the joint distribution of these two random variables? For the joint distribution, let's look at the marginal distribution of this guy. This is truly random. Yeah. And what about D in a product R? D in a product R is precisely D in a product with R plus B E sub x by definition. So you can compute. I'm claiming 2 things. One, you can simulate Bob's message completely at random. And Alice's message is the deterministic function of Bob's message. And therefore, that didn't give me any more information. That's it. Yeah, that's that. So what is the complexity? N, capital N, 2 to the little n on Bob's side and 1 bit on Alice's side. There is a dual protocol, which I won't explain. It's an exercise, which gives the opposite. It's actually even the more simpler protocol in some sense, right? I mean, this is a combinatorial protocol. What I showed you is an algebraic protocol. It gives you the opposite guarantees. And it turns out that you can balance between the two. Whenever you have these things, you can do a balancing trick, and that gives you square root n and square root n. So 2 to the little n over 2 and 2 to the little n over 2. And that was the best known. And on top of this, this protocol has linear reconstruction. All these protocols that I described have linear reconstruction. Yeah, which means that for every d and x, Charlie can write down a linear function, which when you apply to both Alice and Bob's message, you get presumably the bit. Yeah, and we know on top of that, for linear protocols, this is actually the best you can do. You can't, the product of Alice complexity and Bob complexity is omega. Sort of like saying, span programs, the number of rows times the number of columns is 2 to the n. Yeah, so that's good. So this is the state of affairs so far. So what we can show is not 2 to the n over 2, but 2 to the square root n. This is the first sort of improvement. It's the only thing I'll talk about today. In fact, we show not just a protocol, we show a way to take any nice enough 2-server private information retrieval scheme, which I'll define in just a second. You can turn any such protocol into a CDS protocol with nearly the same communication. Okay, so just think of it as a compiler from Zeev to us. Okay, or Zeev and Shivakant to us. Yeah. Moreover, all the 2-server peer, in fact, even constant server peer schemes, sort of multi-server peer schemes I know are nice enough in our language, which again we'll get to in a second. So this is the theorem.
Can you explain what's the connection between CDS and peer?
CDS and peer, I haven't told you. That's the whole point.
Slide,
This is the theorem statement.
okay.
This is not a theorem, it's a note, it's a comment. Yeah, so this line goes right up here.
So you don't actually use the scheme you showed us in the previous slide?
No,
it was
no,
enough.
because that's the best you can do with that scheme is 2 to the n over 2. I want 2 to the square root n.
Okay, so
Forget it. This is just
we use
get your juices flowing. Maybe, you know, maybe you will simulate what I'm about to say, you know. maybe Zev will. Okay, so anyway, okay, good. Private information retrieval, 2-server private information retrieval. Here's what it is. Again, you know, in a 50,000 feet, it looks kind of like there are still 3 parties, right? There's a green one, there's a blue one, green one, there's a red one, and a black one, right?
everything looks like that, you know that.
Yeah. Except you have to look a little bit closer. These 2 guys, Alice and Bob, they don't have a shared random string or anything of that form. They have the same database, the same array. It is, you know, it's replicated across these 2 parties. This guy has an index x, and he wants to retrieve d of x, the x index of the database, and he doesn't want to reveal x to either of the 2 parties. Okay, so he wants to send one message to each of these 2 parties, right? He wants to get one message back, and from this he wants to recover d of x. That's correctness. Privacy says that the marginal distribution of q0, respectively q1, is independent of x. Yes, that's what private. If either one of the 2 servers, if either one of these 2 parties, the green and the red party, looks at what they get, they don't know what the guy was looking for. Yeah? Good. And after a lot of work, you know, the best 2-server peer protocol we know has communication complexity 2 to the square root n, and this is the Shivakant and Zaev paper, 2015. Good, so again, you know, let's look high level, let's zoom out, right? So these guys look very similar from a very high level. In fact, the best known protocols, you know, so again, the best upper bound is 2 to the square root n. This is Shivakant. The best lower bound is 5 times n, you know, for peer. You know, we don't know any better. The best lower bound for CDS is again omega n. And what we are asking is, well, the best upper bound is the 2 protocols I showed you, 2 to the n over 2. I'm asking, we're great at pattern matching, right? I'm asking a pattern matching question. Can we, given how similar these guys look in 50,000 feet, most of the times this doesn't work, but this is sort of one example where, you know, pattern matching actually works, which I'll show you in a minute. Okay, so here's the construction, and I'm going to show construction entirely in pictures, no math. Okay, so here is a peer 2-server peer scheme, and I want to go from here to CDS scheme. Right, so how do I do it? Peer, again, this guy has input x. He sends q0 and q2 numbers to either one of the 2 databases, gets the answer, and reconstructs. Very proud of this. I didn't do anything. I can just think about the person who asks the questions and the person who gets the answers and reconstructs as 2 separate things. Maybe they share a state, but if they do share a state, they can secret share the state across. So I'm going to assume that they don't share states at all at this point. Okay, so now I want to sort of peer into the q0 and q1 and see what they look like. What do they look like? Neither q0 nor q1 reveal anything about the index x. Yeah, and put together, they do reveal the index x at the end of the day. So what are they? They are a secret sharing of the index x, semantically, right? I mean, they don't have to look like it, but semantically they are. In fact, let me extend this analogy and say I want a peer scheme where the 2 questions look like an additive secret sharing of something, of some sort of number, some vector, bit string that depends on x. That's property number 1 of the nice enough number 1. Right? So semantically makes sense. And let me sort of call these functions by names. Let me call this sort of this is a function that the first database computes. It's a function of what he gets. and the database. So H sub D of R. I didn't do anything here. This is just a notational, syntactic sugar. Same thing with the other guy. Yeah. So far so good. So here is nice enough number 2. I want the function that this guy computes, the reconstruction function, to be a linear function for every choice of x. In other words, the way the reconstruction works is he takes x, he computes some linear function, some vector w sub x. Yeah, that's a description of a linear function. And then he computes a linear function on these two guys, and he gets the answer, the xth bit of the database. So that's nice enough number 2.
So the only nonlinear thing here is computing u sub x from x.
Good. So the computing u sub x from x and computing h sub d of r.
H sub d of r may also be nonlinear.
Totally nonlinear. Could be completely arbitrary. Yeah, so I'll call this linear client PIR. Okay, so what do I do with this? Well, now I can start pattern matching, right? This message R that goes from the client to the first database, what is a random message? It doesn't have to send a random message. It could be a shared random string. Why not? It's the same thing, right? That's number 1. I'll call this party Bob, and I'll call this this guy Alice. Yeah. So now they have a shared random string between them. But if you pattern match, yeah, if you try to pattern match even more, Alice and Bob have not just the database and x as inputs, respectively. They also have a bit b, and that's the only thing they're trying to hide if you think about it, right? So what is this bit b doing here? Well, let's see what the peer protocol does if Alice does one of 2 things. Okay, so either Alice sends the peer message, right, or she sends just R. So it's R plus b times ux, right? If b is 1, she sends the real message of the peer. Otherwise, she sends R. Yeah. So what happens to the reconstruction function? You see what's happening to the reconstruction function. It says if b is 0, then these two guys are identical. Yeah, the left and the right are identical, so you get 0. If b is 1, you get the peer answer, which is d sub x. So the answer, in other words, is b times d sub x.
What is wx about?
Say again.
What is wx?
Wx is the description of the linear function that the client computes. So it could be a linear function. Yeah, I mean, I can in general write a linear function in this form. So yeah. I'm also proud of this. Okay, so the 2 parties became 1 party. That's sort of what I'm saying, right? So now this 1 party has enough information to actually be the client, be the Charlie in CDS. So what does he do? He gets h sub d of r, right? Which is 1 answer from one of the servers. Since he knows x, he can compute the inner product of h d of r and wx, right? He knows x. And he gets one of the peer queries, peer questions, r plus bx. Since he knows the database, he can actually compute hd of this guy. So really, I use the fact that this guy has both of these guys written in other people's foreheads. Yeah. Good. And that's that, basically. So this is, well, I mean, I shouldn't have shown this, but anyway, yeah, doesn't matter. Right, so this is a correct CDS scheme. You have 3 parties. 1 party knows a database and a bit b. In fact, he doesn't even use the bit b, right? Again, with the loss of generality. This guy has an input x and a bit b. This guy has d and x, and you put things together. That's it. That's that. The only problem is that this is not private, in the sense that even if d sub x is 0, you might actually end up revealing the bit b. Okay. We have to see. So that's a problem. It's a big problem. Yeah, it's a big problem. Yeah. No. I'm not going to stop here. If you. Yeah. So that's a big problem. Okay. Good. Why is it a problem? You look at the security proof, and that's how you discover problems with all these things. You say, oh, this looks good, very good. Let me try to write down a security proof. It doesn't work. And then you say, well, why doesn't it work? Here's why it doesn't work. This guy actually hides the bit b entirely, right? Because R is completely random, so the marginal distribution is still uniformly random. But what about this guy? He actually reveals some information about the common randomness. In fact, it could be a lot of information. In fact, that information could compromise the bit B, and yeah, nothing. Yeah. So if you look at it again, you see that it is okay for this guy to reveal this string inner product with wx. In other words, the output of the linear function on this guy, that's okay to reveal, again, the same as the arguments we did before, but he cannot reveal the input to the linear function. But then you think you're stuck, because what is the linear function? The description of the linear function depends on x. He doesn't know x. How is he going to compute the? Then you observe that this is a linear function. Linear functions are exceedingly nice, and instead of sending this string, Bob and Alice can run a simple protocol which lets Charlie compute the linear function output, but nothing else. Okay, so that's the final piece to the puzzle. And here's what I'm going to do. I'm going to put more things in the random string. Yeah, doesn't matter. I'm going to one-time pad HD of R. Yeah, so to add a random string to it. So now there's really no information. Yeah, but this kills correctness. How do I recover correctness? I just reveal the inner product of R prime with wx. So if you look at just these two messages, right? Charlie can now recover HD of R inner product wx. That's precisely what you wanted, and that gives you correctness and privacy on top of it. Yes? Question.
Alice got two messages, right?
Yes. So this concatenation of two strings. Yeah?
No, but I mean, now you also need to check correctness again.
You do need to check correctness again. Again, so let's actually do it, right? So this message, Charlie is going to take the inner product of this with wx. So he gets this times wx. He subtracts this, so he gets HD of R inner product wx, right? And then you do precisely what you did before, right? And that's it. Yeah. Right, so this is proof in pictures. And now the question is, in some sense, we've piggybacked on you guys and these guys. The question is, where does this H sub D come from? Where does the peer protocol come from? This I'm not going to sort of get very much into it. It's really I'm just going to put it up, right? This is matching vector families. So what these guys showed is how to take matching vector families and construct a function H sub D which has this behavior. Yeah, so that's what it is. Good. So Avi, I expect I'm running out of time, right?
Yeah, it'll take a
few more minutes. Okay. Okay, good. So I was going to sort of get into the math, but it's simulatable for Zeev. And if you have questions about the math, you should ask Zeev. It's really what he did. Yeah.
So basically, you showed that you can base this CDS
right
on peer.
Right.
And then you get all the nice like you get the complexity from the peer.
But yeah.
What about the other way around? Do you remember that you can
No.
base peer?
No.
Because maybe you don't need all the power of peer, and you can hope to do better than square root.
It's a fantastic question. I don't know the answer to it. We tried. I don't know the answer. So what does it give you concretely for secret sharing? It gives you a secret sharing scheme for these graph access structures that I showed you. The trivial answer, the best known answer was n squared somehow. The n is the number of parties. Now we get n times 2 to the root log n, which is the right number if you translate.
So you have basically two steps. You go from peer to the CDS.
Yes.
And from CDS to secret sharing.
Yes. CDS to secret sharing is actually a syntactic here, because we only looked at a particular class of access structures.
Okay, so you can't include this part. This is.
We'll see. Okay, so let's get to it, right? Math. Okay. Okay. So the second step is to generalize this above sort of graphs. So the CDS gives you secret sharing for graphs. What do I want? I want to make and the number of access structures is slice functions, 2 to the n squared, basically. I want to increase it. What do? I do hypergraphs naturally, right? What is hypergraphs? you have a n-party graph, 2 parties, right? Every set is pick one element of each pair. You know, that's the okay. Let me put it this way. A hypergraph is defined by, you know, a collection of subsets of these 2n people, such that you have at most one party. You have exactly one party from each pair. So it's a particular class of access structure still. And the question is, what is the right game? What is the right communication game that gives you a secret sharing for this this thing? And that's a multi-party CDS scheme. Yeah. Okay. So here's the multi-party CDS. Really, it's the same thing as before. You don't have like double vision. This really, I mean, I really did draw this like 3 times, right? So I take Bob, who used to hold an n-bit string before, and I make it into n Bobs that hold 1 bit each. Everything else remains the same. Yeah, and that's a multi-party series game. Clearly, it's harder, right? Because there are now many parties that hold bits of. Right? So any protocol for multi-party CDS gives you a secret sharing scheme for this hypergraph access structure. So
do you know the other way around?
No.
That this is required?
Okay, so I do know that secret sharing schemes for hypergraph access structures are equivalent to, because this connection is syntactic. That I know. That part I know.
Okay, so what don't you know?
Say again?
So what don't you know?
What don't I know? The connection between peer and CDS is a one-directional thing. I mean, that's still the yeah. That
Second one we do know.
yeah.
So they are allowed. So the dealer, whoever, should get the bit if what? If it's just you concatenate the x subice to an x, and whether the
Exactly.
x is
Exactly. It's the same game as before. I just spread the x across to many parties. And this, again, we can construct a multi-party CDS protocol with the same communication complexity as before. The fact that you spread it into n bits didn't change anything. Yeah, that's the theorem statement. I haven't proved it. That's the theorem statement. Yeah. Okay. So how do you do it? One slide. We want to lift. We already have a good thing going. Why drop it? You want to lift 2 CDS into this n CDS. And in some sense, what you want to do is you want these n parties to run a protocol. It cannot be an arbitrary talk back and forth protocol. It has to be a one-way communication protocol, such that they compute the message that the original Bob used to send before. Yeah, you want to emulate this one Bob by these n Bobs. That's what you want to do. And if you think about what this one Bob did, one thing he did was, the first thing he did was he took the x, the index x to the database, and he constructed this wx and ux, this thing that Zaev does, this description of linear function. That could be a really complicated function. In fact, if you look at it, your head spins a little bit. Yeah. Yeah. So as is, it seems fairly complex. Then you're back in you don't get anything. So the key idea is that if you can go into these matching vector constructions and make these matching vectors decomposable. I haven't even told you what matching vectors are, so it's a bit hard to sort of know what decomposable means. What do I mean by?
You go there and you try to do a distributed.
Essentially. So there's no protocol there. There's a construction which is. So matching vectors, again, you have a collection of vectors. If I take the ith vector from here and ith vector from here, the inner product is 0, else it's non-zero, mod 6, something like that. Yeah. What I want is that one of these vectors could be arbitrary, could be completely arbitrary. In particular, the function that takes I and computes the ith vector could be completely arbitrary. What I want is that this function, this ith vector, looks like a product, a coordinate-wise product of little n vectors. In other words, you should be able to come up with 2 times little n vectors, such that every kind of pairwise, coordinate-wise product gives you the right vector. So that's what I mean by it. It's just the right notion that that gives you multi-party CDS. It turns out that you can actually construct. You can, if you go back to sort of Grolmus, you can construct decomposable matching vector families, and they directly. So same construction, they give you. Good. So that gives you multi-party CDS, and what did that give us? that already gave you, one second. Good. So that already gave you sort of a secret sharing scheme for these many access structures. Why these many? Because you have n parties in total. You pick arbitrary subsets of n over 2, or rather sort of subsets where you pick one from each pair. There are 2 to the n over 2 such sets. Therefore, 2 to the n over 2 such access structures. So you went from this to this already with this technique. The final thing is the two final things. One, we want to sort of take this and make it into a secret sharing scheme for slice functions. So slice functions are more general than these guys, right? So these access structures look like the following. The n parties, you divide them into pairs, and each set sort of is one element from each pair. Slice function says you can take arbitrary subsets of n over 2 parties out of n. So that's more general. So it turns out that we can do that. So this part is combinatorics at this point. There is no peer, there's nothing here. This is combinatorics.
Here you move already from 2 to the root n to the 0.99, whatever.
No, slice functions still 2 to the root n. Still 2 to the. So a component of our proof of our theorem is a secret sharing scheme for all slice functions. It doesn't matter what slice it is, n over 2, n over 3, it doesn't matter, with 2 to the root n. 2 to the root n. And then comes the extreme, so that's the theorem. Then comes the extremely annoying part, and that's, this is where we do this construction of a monotone formula over the slice function basis, which now should make sense because we have secret sharing schemes for the slice functions, for all slice functions with 2 to the square root n complexity. Now we want to build a small monotone formula over this basis, and you're done. But that's where we get hit. So it is an open question how to improve that last, you go all the way until sort of, the finish line minus what we think is epsilon, and then you, I don't know, you get hit with this issue. Nothing. No, to my knowledge, nothing.
Okay, so the last step is implementing general secret sharing using secret sharing for
slice functions, yeah. And that is basic, the way we do it is implement a monotone formula for a general function using slice functions as atomic gates. If you manage to do that, then you can go back to sort of what everyone.
Go back to the certain formula.
Yeah. So that's the way we do it. Yeah.
Okay, so basically the slices are 1 billion blocks that you identify that you can improve.
Yeah.
Conceptually, you can have like a different family that you can improve on and show that it's complete. Potentially. So this is our one approach, and so this talk paper is about where we got stuck trying to do something. At some point, I saw the slices. Where did they come from?
So I didn't tell you how to do secret sharing for slice functions. I only showed you this in detail.
We saw the slices, right?
What do you mean?
Okay, I'll watch the talk.
These are slices.
Why do you use slices as opposed to something else?
Something else. Slices follow naturally from this construction. So this construction gives you secret sharing where each set in the access structure is one out of every pair, which is a slice, basically. Exactly one out of each pair, which is a slice. Okay, so I don't want to take too much more time. In fact, I can tell you what it is offline, but at this point, it's combinatorics. Good, great. So that's the one part that I wanted to sort of get to you is how to go from peer to secret sharing. Number one. Number two, there are these interesting questions. What I think are interesting questions, which have nothing to do with cryptography. You don't need to know anything about cryptography. You can think about it, and we will love you for it if you solve it. Yeah. So there are many other questions along these lines. I think of this sort of general question of why does communication cost have to depend on computational cost in cryptography as a completely fundamental question. In the information-theoretic regime, we have no answers to this question. On the other hand, if you're willing to make computational assumption, there is this beast called fully homomorphic encryption, which gives us a protocol for all these things where communication is independent of the computational size. So if you make computational assumptions, you're good. But the real question in my mind is sort of the information theoretic question. We know several things in this world. We know, okay, you can watch the video, but roughly speaking, private information retrieval or locally decodable codes equivalently are the bottleneck in many of these things. Either they are the real bottleneck in secure multi-party computation. There is a both-way connection. If you can get better secure multi-party computation protocol, there's a better peer scheme and so on and so forth. In the other cases, it's an apparent bottleneck because the best way I know to get a CDS protocol is going through PIR. So it's not like I have a connection in the opposite direction, but seems like a bottleneck. And that's that. Thanks for listening.